Hey everyone, and welcome to another CTF Writeup video. Today I'm going to be talking about the challenges from nullcon HackIM CTF 2023. It was a 24-hour CTF run as part of the nullcon conference, and overall it was a lot of fun. I thought I was only going to play for maybe an hour or two, but I ended up spending all day on it, and we got 10th place, which was pretty cool. Like I said, I'm going to cover the challenges that we were able to solve, and then also talk about some of the challenges I didn't solve. I'm going to skip the hardware section because this was on-site only, so obviously I couldn't do those, but we'll talk about some crypto challenges, some misc challenges, pwn challenge, cloud challenge, rev challenge, and a web challenge, or 2 web challenges. So yeah, let's get started. The first challenge is twin crypto. It says the twins Alice and Bob are so close that they share everything, even the modulus of their RSA key, and we're given a download file. So the challenge already told us what the solution is. We're going to be doing a common modulus attack, but let's take a look at the download files. So we're given a couple different files. There's a chal.py. This is going to open up the 2 other key files. It's going to do standard textbook RSA on using both of those key files, and it's going to encrypt the flag both times, and then it's going to write out the ciphertext. And so we have the 2 public keys, we have the corresponding ciphertext, and so we are set to go. Like the challenge text said, they're using the same modulus, so the same n. And because of that, there's an attack on RSA called common modulus. And so we just need to perform that attack. Let's go to the solve script. So here's the solve script. We're going to import those same 2 keys. I print out the values just for debugging and a little sanity check to make sure that the modulus is actually the same. Here are the 2 ciphertexts. If you're not familiar with a common modulus attack, I highly recommend reading this page by the crypto book. They do a really good job of explaining it. It's a very common CTF sort of challenge. The only difference between what's written here and the one we're going to do on the CTF is the GCD of E1 and E2 is not equal to 1. In this case, it's equal to 17, I think. And it doesn't make it too much harder. For this case, it just means we have to do a root, a 17th root at the very end of the challenge. But again, if you're new to this type of crypto hack, I highly recommend checking this article, and then also just go to crypto hack and do the challenges. They're amazing crypto challenges, a great learning resource. Anyways, so we're going to do the common modulus attack. Really, it just involves doing this extended GCD. We're going to get out these 2 values, and then we're going to raise the ciphertext to those 2 values, multiply them together, and then I said the only difference between a normal common modulus attack where the GCD is equal to 1, we're just going to do that I root at the very end with the G, which I think is 17. So then we just do Python 3, solve, and at the very end we get the flag. So fun quick challenge. The next challenge is bmpass. That says, my brother thinks he's some kind of genius and stores extra passwords in the image file before encrypting them for extra security. It's been getting on my nerves lately. Please prove him wrong. We're given 3 download files. So this is the encryption file. It's going to import AES, it's going to open a file, it's going to pad it, it's going to encrypt it using a key of 16 random bytes with ECB, and then write out the file. We're also given that README file, which is the same, and a encrypted flag. So if you've seen this before, it's pretty easy. Since we're taking in an image and we're just encrypting with ECB, anytime there's 4 blocks of the same information, they're going to encrypt to the same 4 blocks. And so you'll be able to see a pattern. There's a very famous image of this called the ECB penguin. You can see it here. So the ECB penguin was encrypted using ECB, but because a lot of the pixel data is repeated over and over and over, it's going to encrypt to the same ciphertext. And so you can still see the contents of the message. So you go to GIMP, you select open file, raw image data, and then you select the file, and make sure you do show all files. We'll load it like this. Then we'll load a RGB alpha. We want it to be 16 bytes, so it's important that it's 4-byte aligned. Then you can play with the offset a little bit. I think for this case, I found that offset 1 worked best. And then from there, you just play with the width until you get something that looks readable. And so as I'm zooming out, you might be able to see that like it almost looks like little structures are forming, like those red lines. And you can definitely see a pattern. Like if this was real output, like right here, you can almost see something. It doesn't quite look like text. You know that there's going to be something in there. And so we're just looking for the correct offset. The lines are kind of lining up, and we go bit by bit, and there we have a message. So let's make it a little bit longer. The hard part actually was getting out the flag. So this is actually upside down and reversed for some reason, but the flag format was ENO bracket. And then if you read it, what I did at this point is I just take a screenshot It's going to save to the desktop. You know, I could just do this in GIMP now that I think about it. I don't really need to use this, but come on. Oh yeah, it wants me to close GIMP first. So then we can rotate twice, and then I think it's tools. We're going to flip horizontally. There we go. And so it's still a little bit difficult to see, but ENO, I can see through encryption. And that was the flag. The next challenge is breaking news. It says, Al started to encrypt the flag, but realized halfway she was unhappy with her key, so she created a new one. I did not solve the challenge during the CTF. I spent a lot of time on it, and now that I see the solution, I'm pretty mad at myself. But yeah, let's get started. So we're given a couple different download files. The first one is chal.py. It's going to, again, import two keys, key1 and key2.pem. It's going to split the flag in half. So we have message 1, message 2, just based on the flag length. And then it's going to encrypt both of those and give us the ciphertext. So seems like a difficult challenge. The first thing I did is I started printing out the values. So Python 3, solved.py, just to show the start values. So if we look at key 1, the E value for key 1 is pretty large. We can see like absolutely huge and pretty close to N. And so when you see this, I usually think of Wiener's attack or Bona's attack, Bona-Dufrie's attack. Both of these are attacks when the D is small. And if E is large, it's not guaranteed that D is going to be small, but it's something to start with. So to do this, you can use a tool called RSA CTF tool. There's also a whole bunch of implementations online for doing all these attacks, but what's nice about RSA tools, it's just going to do a bunch of other attacks for you at the same time. So we're going to pass RSA CTF tool the public key, and we're going to ask it to dump out the private key if it finds one. And we're just going to try on key1.pem. So we run it real quick. Again, it does all these attacks, and we can see it was the Wiener method, and they dumped out the private key for us. So cool. We have the private key for part 1. This is where I got stuck, and I spent many hours trying to figure something out. I thought we had to do a similar attack for key 2, so I started playing with the Bona attack, because E2 for key 2 is also very large, and so I assumed D2 was going to be small. And so in the Bona attack, you can do like this LLL matrix, and you have to reduce it, and I just was playing with larger and larger matrices trying to get something to pop out, but it turns out it was way simpler than that. All I had to do was look and see that they used the same N values for both of the keys. So they said they generated a new key, but really they only generated a new E for the key, or a new E and D. It's still the same N, but because we already cracked the first key, we already know the private P and Q for N, so we've already cracked both keys. So really a simple challenge once you realize that. I just didn't pick it up on the CTF. So anyways, this is the solve script. Like I said, we take that private key, we're going to put it into a file. I dump out the values just to take a look at them, as we saw earlier. I'm loading in the ciphertext. And so for M1, since we have the private key that we were able to crack with RSA using the Wiener method, we can just decrypt part 1. For part 2, like I said, since we have the private key, and so the security of RSA relies on factoring that N. Since we have the factors of N because we have the private key, we're just going to pull out those factors out of the first key, and we're just going to construct a new private key for part 2. So to do that, I pull out Q. For some reason, it didn't have a P value, so I just constructed it. So Q1 divided by N divided by Q. Assert that P and Q is equal to N. So now we have the P and Qs that build up the N. From there, we just need to calculate what D2 was. So we take the E from from the second key. We do a mod inverse with the totient. Then we construct a key. So you can do rsa.construct and pass in a bunch of values. I just found these online somewhere. Do I still have it? Oh, yeah, here we go. I had to look it up, but it's called construct, yeah. So when you construct an RSA key, you just need to pass it some values. I saw that you just need N, E, and D, and from there it'll construct the rest of the key for us. So we pass it that key, and we do decrypt. And you probably saw earlier, both parts of the flag popped out. So not too bad of an attack. We just need to do the Wiener's method and then realize that the keys were using the same N, and then from there we just construct the private key material and we get out the flag. The next challenge is Crypto Collector. It says Bob is hosting a party, invited everyone but me, but all the invitations I can collect are encrypted. We're given a netcat port and a download file. If we look at the download file, there's two functions. There's actually two parts to this challenge. The first one is if we scroll to the bottom, it's going to generate an RSA key. And we can see this E, it's going to be generated from random values between 0 and 4. So a little bit strange, but so that means E's will have values of like 3, 5, 9, a couple different small values, which is useful. It's going to call this weird pad function, which we'll come back to a little bit later. Basically, this is just going to do a bunch of very strange XOR math with a little sprinkle of randomness. But once we go through this, this will be part 2, we'll find out that the randomness isn't really random, and you can actually reverse all this XOR math. But anyways, it's going to do all that XOR math on the flag, encrypt the flag with that RSA key that was generated, and it's going to print both of those out. And so if we go to the netcat port and we connect to it, it's not an interactive netcat port. It's just going to dump out a new public key and some ciphertext. So because these E's can be small and they're going to be reused, we can do something known as a hastad broadcast attack. And the other thing that we need to is we actually need to look at the pad function, and we need to see that it generates the same bit stream every time. That's also important. So because we have the same message, we have the same E's, we're able to perform the RSA attack known as hastad's broadcast attack. And basically this is an attack just doing the Chinese remainder theorem. Yeah, that's all there pretty much is to it. If you want to look up the attack, I'd recommend Googling for it, but basically we're just going to be doing a large Chinese remainder theorem. So the first step to this is we need to download a bunch of these public keys and the corresponding ciphertext. So to do this, I just wrote this little script. It's going to connect 30 times to the remote port. It's going to receive all, and then it's going to save the note. And that's pretty much it. So you run that, and then I have a collection of 30 notes. And so each one of these notes is going to have, like I said, a public key that's going to be using a E of either like 3, 5, 7, 9, something like that, and the corresponding ciphertext. From there, I read in all the notes, and I clean them up a little bit. Some of the key string was a little bit weird, but once you can do that, you can do an RSA import on the key, and I keep all the notes that we're using E is equal to 3. Cool. At this point, so we have a collection of ends for all those keys, and we have a collection of the outputting ciphertext. And like I said, we're doing hastad's broadcast attack. I just copied this code from online somewhere. But yeah, basically you're just doing the Chinese remainder theorem on all of those. And at the very end, you have to do a cubed root. And if you do that correctly, you should get back the message. So that was step 1. But like I said, the message was encrypted using this very strange function. I'm not going to bore people with the details. If you want, you can go through this thing and just kind of rearrange terms. It took me maybe like 20 minutes of just like playing with a pencil and paper to actually understand what this was doing. But we have the output of this. Using the hastad broadcast attack, we were able to get what the output is. And from there, you can peel off some values. So you can peel off this mass DB value and peel off this mass seed value. Like I said, you just kind of go through piece by piece and you're able to encrypt it or decrypt it. This tag parameter is never used, so it's just an empty string. So it's going to do like the SHA-STUM on an empty string. This stream is the flag. You never actually recover it from here, but the flag is also being, stream is flag. It's being used over here too, all the way over here. So like I said, you just kind of go through, reverse the XOR math, and you get out the flag. And so this is what the solution looks like. There was that pad function. I just called mine dpad. Like I said, I strip off some values. I generate the different seeds and the random bytes and stuff. And then at the very end, you'll get the flag. So Python 3, solve2.py. And there we go. This was the resulting output. And we can see here is the flag. So fun little challenge. I think the hastad broadcast attack part was fun. I'm a little bit confused what the XOR sort of math was supposed to emulate, but fun challenge. The next challenge was babyrand. It says, look at how many hints I'm giving you, how hard can it be? And we're given a netcat port and a download file. If you look at the download file, it's going to do something 100 times. It's going to give us 32 bits of random 9 times in a row, and then it's going to ask us to guess the 10th one, and if we get it correct, we get the flag. And like I said, it does that 100 times. So in total, we're going to be given 900 bits of randomness. Sorry, 932 bits of randomness, and we just have to guess a couple of times. If you've been playing CTFs for a while, you probably know that you're able to reverse the Python random function if you can get the output of 624 calls. This one's a little bit trickier. Normally you need 624 consecutive calls and you can like instantly figure out what that initial seed was, or the internal state is. But this one, it's going to read from randomness on every 10th call. So it makes it a little bit trickier, but thankfully there's this beautiful Python script. I don't know who wrote it. Every time I see it, it's in like a gist or something, but there's this file called untwister, and you can find it from just Googling it. And what's amazing about this is you're actually able to input, it uses Z3 under the hood, and you're able to input question marks for values you don't know. And so using this, the challenge becomes pretty trivial. We're just going to send question marks for every 10th randomness because we don't know what it is, and so that way we can just continue the stream. So this is the solve script. We're just going to create that twister object from that untwister file. Then we're going to receive, this is just pwn tools, we're going to receive all the hints we can. And the untwister file expects everything to be in binary. So just when you submit it to the untwister, just make sure it's in binary format. And then whenever we get to the guess, we don't know what the guess is. So we're just going to send a bunch of question marks and tell twister that we have no idea. We do that a whole bunch of times. And on the very last time, we say, hey, twister, generate a random Python random object for me. It's amazing. Twister will just generate a Python random object, and then you can say that new random object, get me the next output of 32 random bits. You send it to the rope file, and you'll get the flag. So we can run it real quick. Python 3 solve. I think this is for some reason my Z3 solution is a little messed up. It takes a while for it to actually run, and we're running it against remote, so it's connecting and doing that 999 times or whatever. It got all the hints. Now Z3 is running and trying to solve the flag. And cool, it was able to figure out what the flag was, and there we go. You graduated Rand Academy, so fun challenge. The next two challenges were actually the same challenge, randrevenge and randrevengerevenge. I'm guessing in the initial version there was probably an issue, a PHP type confusion or something, and so people were able to cheese it, so they released a randrevengerevenge. Same challenge. I did it correctly the first time, so the solution worked for both of these. But for Rand's Revenge, it says only psychics and wizards will be able to complete this one. Sorry, we're given a website, so we can go to that. Oops, let's grab all of it. No, I already have it here. It gives us a bunch of different random values. This one looks like a timestamp. The rest don't look recognizable. It says good luck, and that index.php file. So if we take a look at index.php, there's two different parts to it. The first part is, this is actually the second part, so I'm going to skip that for a second. This is the first part. So it's going to seed srand with a random value. It's going to give us the time. So we saw the time earlier. It's going to give us the first output of random. And then based on some conditions, if like randomness and time are equal or something, it's going to give us another random value. Otherwise, it's going to increment the random stream. And then it's going to save the next output of random to next. And the 60 seconds into the future will be expiry. So that's normally what's called. If we make a post request to the submit route, this code is executed, and it says it'll check and make sure there's an expiry. It'll make sure that we did it in 60 seconds, and then it's going to compare the value we give it with the next value of randomness. And if we get all that correct, we get the flag. So very similar challenge to the Python one. We're just breaking a random number generator. It's really not too bad. This challenge is maybe in some ways even easier. There's a well-known PHP tool such that if you have the first output of a random value after a freshly seeded random value, you can brute force the initial seed, which is pretty crazy. It was a tool written by OpenWall. I'm guessing maybe there was a implementation before that, but the one I'm using is by OpenWall. It's just called PHP empty seed. You get the source and you just type make build and it'll run. Yeah, I think from there, so we need a couple things to solve this. First, we need a solve script. I wrote this in Python just using the request library, so it's going to make a request to that website. It's going to grab the contents, it's going to print it out, and then it's going to wait for what the correct solution is, and it's going to submit that back with the cookies and everything, and it'll tell us what the flag is. I also use a solve.php just to figure out which seed is correct. So PHP empty seed will generate a list of possible seeds, and we don't actually know which one is correct. So we're just going to copy them over real quick and test them to see which one it is. We also need to update it with the correct time. So instead of the Python's or the PHP script was calling time at the start and it was giving us that time value, so we can put it here and use the correct seed. And so basically we're just going to run the solve script a couple different times with the different seeds until we get one that has the correct solution, and then we'll print out the solution and we'll give it back to our Python file. And with that, I think we're all set. So we'll run Python 3 solve. Let me get all the commands ready because we only have a couple of seconds or 60 seconds to solve it. But let's make sure this works. Cool. And PHP empty seed, and let's give it a random, we would be giving it this value. This is the first output. Oh, I found a whole bunch of them. There we go. Oh, I think it's just, I might make this a little bit smaller, sorry. Cool, and these are the different values. We're using Python's above version 7, so if we look at the output, there's a lot going on. But if we look at the output, it says these are possible seeds for these PHP versions. And we can see here's a PHP version that's 7 above. I think if you just test a couple values, eventually you find out that it's going to be one of the ones above the PHP 7. So we'd be testing this one and this one. Cool, I think all of our tools are ready to go, so let's give it a shot. So first thing we're going to do is we're going to copy over the timestamp. We're going to put that here. Then we're going to copy over this random value. We're going to give it to the seed cracker. It's going to start cracking values. We probably should have actually done this one first, but we have 60 seconds. Here is a PHP 7 one, so we're going to test this. We're going to put this as the seed to random. We're going to run that file. We're going to see if they match. We're looking for a 1913, 1913, 198. Oh, we got it correct on the first one. So we'll copy the solution value, we'll place it here, and we'll get the flag. So really not too bad. Normally I have to try 2 values or 3 values. You can see there's another one here, but we got lucky with the first one. And like I said, it worked for both challenges. This was the correct solution. So really all the heavy work is done by PHP empty seed. Nice little tool. The next challenge is spygame pwn. It says, I had fun, made a simple game, blah, 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 Python and C. We're given 4 download files and a netcat port. This is the game file. It says, let's play a simple game. I'll give you a list of numbers. Your guess is to guess which 2 are swapped. There's 2 different modes, easy or hard. You only get the flag if you do hard mode. But if you're able to beat hard mode of the game, you get the flag. What's fun about this is, so they said it was a mix of Python and C. So the actual game mechanics are written in C, which are called by that Python file. I know you could do this, but I've never actually seen it done before. And it turns out it's way easier to embed C code into Python. If we look at setup.py, it looks like all you really have to do is this extension modules, call the module a name, and then give it that C file. And from there, you have to do some Python specific stuff. But from there, all they do is just import spy and then call spy hard and easy. So cool. Not related to the CTF, but I didn't realize it was that simple. Anyways, so the spy module.c, this is where the actual game is defined. Like I said, there's an easy and hard mode. Basically what's going to happen is, maybe we can just run it, Python make Ubuntu. Python 3, we got to install it, setup.py, install. Cool, Python 3, game. Let's do hard. Ready? Yes. So it's going to give us all these numbers, and we have to figure out which ones were swapped. But it's using a random number generator that's guessable, so you can actually figure out what the solution is. But let's just do index 2 and 3 were swapped, and it'll tell us that we were incorrect, and it took us this many nanoseconds to solve. And so basically, we're just trying to guess which numbers were swapped. And ignore that debugging thing, that's something I wrote. So basically, we're just guessing random stuff. But of course, this is a pwn challenge. It's not actually about playing the game. So instead, so like I said, this is the this is the game. It's going to generate a bunch of numbers, a bunch of local variables. It's going to iterate. We get to play this game 8 different times. And like I said, it's going to swap some numbers. The numbers are the same every time due to the randomness. It's going to calculate the start time, calculate the end time, get our inputs. It's going to do a stringed along with our swaps. And then this is the input we gave it. So we're now going to swap 2 numbers. And if the swaps work out correctly, we answered it correctly. Which the actual bug in this code is that the swap variables are unbounded. And so we can actually swap any 2 values we want in memory. Because numbers is just some array pointer, and this is just going to calculate some offset into it. And so basically we have a arbitrary right because we can do that swapping. And this triple XOR thing, if you're not used to it, this is just a way to swap 2 numbers without creating a temporary variable. It's fun little math that's fun to go through if you've never seen it before. Anyways, so using the swap mechanics, and since we control swap 1 in and swap 2 in, like I said, we can do an arbitrary right anywhere. So it seems like it would be very easy to solve this challenge. What makes it difficult is these are the win conditions. So if you win if count is equal to 256, so this is the input into the function, this means hard mode, this means easy mode. If the total OK, this is how many times you're able to guess the correct swapping. Total OK needs to be equal to 5. And if total nanoseconds is equal to less than 1,000 or less than 60 seconds. So this challenge, what makes this challenge difficult is it's easy to get total OK to equal 5. What's hard is to get total NS to be less than 1,000. So nanoseconds, that's 10 to the 9. So like there's milliseconds, and then microseconds, and then nanoseconds. Less than 1,000 means 1/1,000,000th of a second. So playing the game normally, there's no way you would ever get it to less than 1/1,000,000th of a second. I can't even execute the script within 1/1,000,000th of a second. So we have to figure out some way to bypass this total nanoseconds thing. Like I said, I didn't solve it during the competition. I tried a whole bunch of stuff. Like I said, we can write anywhere in memory using the swap mechanic. And so I was trying to overwrite the total nanoseconds thing and the artns and startns and all that sort of stuff because we can launch GDB. Actually, let's just do that real quick. Cancel this. tmux python 3. I think it was solve back. Yeah, this will launch GDB. Let's break on spygame. Cool, okay. It's a little ugly since it's so big, but basically we are in the spygame function now. And so if I do next, now we can print out the address of numbers. That was that number variable. This is where numbers exist on the stack. And we are allowed to offset anywhere relative to this. And so we can figure out what the address of any of these other variables are because they're going to be at some known offset away from this value. So if we wanted to overwrite the value I, so we would print out the address I. It's not, I is a little bit weird because it's that loop variable. Let's say swap 1 for some reason. Maybe it's not defined either. Let me go next. Okay, I is now defined. Print I. If we wanted to overwrite the I value, we would just figure out the difference between this I value and the numbers value, and we would do that swap. And since the way they construct these matrices, if you remember, it was printing out every number between 0 and 256, we can swap with any of those values, and we basically get an arbitrary byte overwrite. It's arbitrary byte write. But like I said, it's not that trivial. We need total NS to be less than 1,000. And every time it's going to be adding, even when I run it locally, I think it adds like 50,000, around 50,000. And if we do it over the network, these servers are located somewhere in Europe. I think it was like based off of a different challenge, it was like US Europe 1 or something like that. And I'm in New York. So just the latency is going to be insane. We're probably going to talk about roughly a second per request would be my guess, or maybe a half a second per request. So this total nanoseconds is going to be like, we're going to be adding 10 to the 8 every time. So that's tricky. I had a couple of ideas, but like I said, I did not solve the challenge during the CTF. The person that did solve it, what they were able to do was, and a couple other things. Total NS is also a unsigned int. If it was an unsigned int, this would be trivial. I feel like that would have been a fun way to make this challenge, is to make it an unsigned int, so you just need to overwrite that top byte, and it'll be negative, and so that way, it'll always be less than 1,000, so you only have to do that overwrite byte once. But the person that did solve it is they were able to do a wraparound, and they were able to kind of calculate such that they know the next one will be, they calculate, like I said, they're going to do a wraparound, so they're going to set the high bits of total OK to equal to FFFFFF, and so that way the next call that they make will wrap around and get it less than 1,000. I think they must have been, maybe I'm misunderstanding, but I think they must have been very close to the app server, because still to get it less than 1,000, like you're still talking a precision of 1 in a millionth of a second. That's insane. Like when my network requests take half a second, there's no way I'd ever be able to get it to 1 millionth of a second. Like I'd have to run it like 5,000 times, which just doesn't sound that fun. That was one solution. The other solution that I'm pretty sure is possible, but I didn't actually end up implementing, is since you can overwrite this I variable, you essentially get you can execute this as many times as you want. You just overwrite this back to 0 whenever you want, or, negative a billion. If I is unsigned, it's not. So, just to 0 whenever you want. And you can use it for arbitrary reads and for arbitrary writes. And so now we have unlimited arbitrary reads and arbitrary writes. And you get arbitrary reads because, with the relative offset, because you can just swap a variable. And so wherever variable you're swapping within your array, you'll be able to see what that result was. So we have arbitrary reads. So then we can take the elf section. So spy module. That's nasty. If we go to this data section, so this is VM map. If we look at the data section for spy module, let's print out 200x at this address. We can find the global offset table for the spy module. So we can read off some of these values, and that'll give us info leaks to libc. It'll give us a info leak to the main elf, and it'll also give us, we can also read values off of the stack. So we have now info leaks for all the major sections we need, and we can write anywhere. So from here, it's just like a very standard pwn challenge. I don't see why we wouldn't be able to then either write some wrapping code on the return address, then just get shell on the box. We could also maybe do a one gadget and just overwrite one of these entries. Someone in Discord said they tried it and they weren't getting a callback, so I'm guessing maybe they're hitting the alignment issue. I'm not really sure. But yeah, then you could probably just do a standard pwn challenge. Like I said, I was pretty tired, so I didn't end up doing it, but those are two different solutions. Like I said, the solution that someone else did, this was an exploit by minigoat. I'm sorry if that's not right. Maybe mini3oat. Like I said, they just overwrote the high bits of that total ns function, and they were able to get that wraparound such as less than 1,000. And so they just did the high bits for 6 different bytes, and then that last one they found out that the value of 232 would give them the overwrite they needed. It seems like it would not be reliable, but maybe I'm missing something. But anyways, decently fun challenge. I think the ideas were cool. It's just getting that less than 1,000 seemed unnecessarily difficult. The next challenge is Rev Pythopia. Can you find your way through Pythopia, but you need a valid license to enter the city first, and we're given a download file. So if we open this up, oops, we're given this, where is it? This AST, so abstract syntax tree, and it looks like just a Python dump of an AST. So Python has this AST package, and you can load in some source code, and it'll just dump out the AST for you. And this is what it looks like. I loaded this back into Python, AST dump, just so we can get some syntax highlighting. So if you do from AST import star, it's the same file, just now we have syntax highlighting. So AST actually has a way to, the Python AST package has a way to load AST back into a valid Python script. I couldn't get it working though. I'm wondering if they modified this slightly so it just wouldn't import, but something about a with statement, it just wasn't working. I tried a couple different versions of Python. Maybe I was doing something wrong, but thankfully this code really isn't too bad, so we can just read it by itself. So I'm pretty much just gonna skim over this AST. This is how I solved the challenge when it was going on. Like I said, it wasn't a hard challenge. We can see it's importing OS, so nice and simple. We can see it's doing OS path exist. It's looking for a license.txt, nice and simple. Sys exit, so it couldn't find the file. If it can find the file, it's going to open license.txt with a with block, and it's going to assign, it's going to read it and assign it to variable key. I'm not able to like read all this syntax tree, you see the keywords and you know it's what it's going to do. It's going to check the length of the key. It's going to make sure it's equal to 64. So we're looking for a 64 byte key. It's going to assign key 1 equal to, looks like it's doing a slice of 16. So key 1 is 16, then key 2 is 16 to 32, key 3 is 32 to 48, and key 4 is 48 to 64. So it's going to be 4 equal chunks of key, and we can kind of guess from this, from now on, it's going to do 4 different types of checks on different parts of the key. So we have this class called key checker, a init function. It's going to take in a k, blah blah blah. We're going to do some sort of assignment to variable k. It's going to call upper and lower, a little bit strange, and it's going to compare it against you solved it. And it has this little bracket at the end, so we can take this and we'll just put this in a solve script somewhere. What is all this? Oh, ignore that. Kind of ignore this, but so we have the last part of the key. Cool. Blah blah blah. Nice and simple. Then it's going to, let's see, it's going to take key, it's going to look at the value 0 of the slice of key, it's going to see if it's equal to e, then it's going to take key, it's going to check slice index 1, see if it's n, and then o, and then bracket. Okay, so it's just going to check slice index by slice index, and if you go 4, it does go incrementally, so then we have L, 1, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, blah blah blah, and it checks to make sure they're all okay. Obviously during the CTF you need to check and make sure that they're all the correct slice indexes, but they went in order. It was nice and simple, and it's going to make sure all of those matches, and from that we can get this. It was ENO L1333333. Sweet. The next one, we have a value list, so it's going to create an array of all these values, and then it's going to enumerate through all of them, and then for key 2 it's going to still doing a for loop. Here's the body of the for loop. It's going to do an ORD on the key. So it's going to grab, the ASCII value for each of the key values. It's going to compare them, but there's also going to be a XOR, so a bit XOR with the value of 19. Cool. So we need to grab these out. So I think to do this, I just put it in here. Then I do we'll do all. We'll put them all back. I mean, this is just, value swapping. We'll do that. Value is equal. Basically, I just did this. You replace with zeros. You grab the end. You then put it all into the same line. So you have a little Python array. And then you take the array. And I think this was it. Yeah. You just take the array, then you do a join. It needs to be XORed. If you do it without the XOR, which is what I did at first, I didn't see the XOR, you get this random stuff, so you know something's wrong. But then if you do a join with all of these, you do the XOR against 19, you'll get 7 super duper okay. And we know that was key 1. And then we still need the last key. So if we go through, this was all part of that XOR thing. And then the very last one, we can see it's going to do going to load this in. It's going to do a compare. It's going to grab the slice, and it's going to use a unary substitution operator with this. Basically, that means it's just going to reverse the string. So like in Python, if you do that -1, so like Python 3, actually, we'll just solve it right here. Actually, let's do it clear first. Module is not defined. That is strange. Oh, because we have an ast.py. Okay, so it's trying to load the ast.py locally when we shouldn't be doing that. But anyways, we'll do a is equal to, it is all sorts of jank. Let me rename that real quick. This is why you shouldn't be using standard Python names like that. Do we still have it? No. Where did you go? Is this the AST? Yeah, good enough. We needed that last value, which was a bunch of weird stuff. Yeah, this one. So we say a is equal to this. And if we do a, like I said, with that -1, we'll get LLL nullconf CTF. And we grab this. Cool, from this we have all of the values we need. This was the last one. And if you join them together into one long string, that was the flag. So pretty fun, just going through the Python abstract syntax tree and figuring out what the flag was. Like I said, you could probably, if you're smarter, actually reverse the syntax tree and run it or brute force it. But for this challenge, it was pretty easy just to read the syntax tree and figure out what the flag was. The next challenge is rev wheel. It says, can you stop the wheels at the right time to win? And we're given a download file. There's only one file in there. It was this wheel binary. And if we run it, it says definitely not. If we pass an input, it says nah. If we could pass a bunch of input, it continues saying nah. So definitely something we need to look at in Ghidra. So here it is in Ghidra. You just go to the entry function. In here there'll be main. I think I called it main. Cool. Looks like one big function. We can see a couple of exit conditions. You got it. Nah, definitely not. There was no netcat port, so it means somewhere in here is the flag. So this kind of means it's like a license key generator sort of challenge. So we need to pass it the correct flag probably. Just quickly scanning over it, we can see it's doing some thread start. That makes it tricky. So normally on these license key generators, I just send it to Anger, but with threading, I don't know if Anger can handle threading, so I didn't end up doing that. But going through, we can see it accepts one argument. It's going to do a string length, so the input needs to be 1B, so 27 characters long. Like I said, the first time I went through, I went and reversed a bunch of this code. It's doing a bunch of math. I don't actually know what it's doing. There's a cheeky way to solve it, which I'll talk about in a second. But yeah, it's going to call it to a bunch of functions, do, a bunch of weird pointer math and stuff. Again, more threading and mem copying and a lot of stuff that I'm just not really interested in reversing. Like I said, I'm pretty lazy, so eventually I saw down here, it's going to be doing this comparison with this data value, pfvar1, and it's going to check if it's equal to 0. So what's going to happen is this code is going to spawn a bunch of threads, and it's going to do 1 per character. This is just my guessing from my very quick reversing. 1 per character, and the thread's going to do some pointer math on some data value and the flag. And at the very end, it's going to check this global array, and it's going to see if each value in this global array is equal to 0. So what I did is I played with it in GDB, and I saw that if I type in the beginning of the flag, we know the flag is going to start with ENO and then that bracket. If I type in the beginning of the flag correctly, the first couple of values in this data array are equal to 0. So we know it's doing character by character, which makes this problem so much simpler. We can kind of guess it's going to be character by character with this threading. You don't want to be touching the same data values in multi-threaded context, but I mean you can. But thankfully it's just character by character, doing some crazy math something function, and then if we get it correct, it'll set it. But since it's character by character, that means we can brute force it. And so that's what I ended up doing. So I wrote a little GDB script, but actually first let's take a look and see what it looks like. So GDB, oh right, so it's 27 characters. So here's 27 characters. If we do 27 characters, it'll say nope instead. Let's copy this. We're gonna load it into GDB. Let's break on, puts is at the very end, so let's break on puts. And we're gonna run with that input. Cool, so we're at puts. We can finish puts. And is this still puts? No, 5, 6. We're in the main function. All right, cool. We need to figure out where this address is. So let's do a VM map. Oh, this is huge. Make this a little bit cleaner. We can actually do pybase is a better function. So that's where that is. And we want the pybase to this. Pybase. Oops. So this will calculate where that that data section variable is that we're going to compare against 0. And if we print it out, did I do that correctly? Sorry, let me check something real quick. I think it's just pybase 0x48. Yep. Oh yeah, that's right, because we did everything wrong. We can see, so if we look at that, it's going to compare this arrays against zeros. And we can see none of these equal zeros because we ran it with this, and most likely this is not correct at all. But if we then run this with 1, 2, 3, 4, ENO, this, we run it like this, we finish, then we do a pybase of this, we calculate, we look at 20x of this now, we'll see that the first 4 are 0. So that means it's just going to do character by character. We know the first 4 characters are correct, and the first 4 entries are now zeros. And so we can see that, again, character by character, it's doing some weird math sort of stuff. We don't really care. But at this point, we can just start brute forcing characters. So like for an example, if I didn't know that this character was this, we run it like this. We then check the pybase, copy, examine x20. We can see that only 3 of them are correct now instead of 4 of them. And so now we can just brute force this one character by character until we get the correct value. So I wrote a little GDB script that does that for us. This is what it looks like. We're going to load the file. We're going to break on puts. This is the known prefix, eno, fl. You can delete these. The required length. And basically, it's just going to go through character by character. Actually, let me start running it because it's going to take a while. To run it, you just do GDB. We're going to do it quiet. We're going to execute solve.py. It's going to run in the background. It spawns all these threads, which is kind of nasty and loud. But yeah, it's going to go through character by character, and it's going to try eno bracket A, eno bracket B, eno bracket C, and it's going to see when I print out the pybase, it's going to grab that pybase like I was just doing. It's going to count how many of them are equal to 0. And the one with the highest amount of zeros is the one with the flag, because I was able to guess what the next entry is. Again, there's more efficient ways to do this. This is, again, a very lazy, easy way, but it didn't require any thinking, and I don't like thinking, so it was nice and simple. Like I said, it's going to be a little bit hard to see. Maybe I'll wait till it finishes one round. Okay. No, I can zoom up. So let me zoom up here. So in this execution, it said it's trying to guess. It thinks the current guess is eno bracket f exclamation point, where I'm testing character exclamation point, and it said that it found 7 chunks of 0 at this pybase. Cool. And so exclamation point is the very last one. And it said here that the best guess wasn't exclamation point, the best guess was actually an L. And so if you do eno bracket FL, this gave 8 zeros. So we know that L is the next character in the flag. Like I said, so now it's just going to do FL. I think the next character is probably A for flag. So it's going to try A, B, C, D, all the different ones, and it's going to see which one has the highest count. For that one, it should be 9, because it'll be 1 more. And it'll just do that character by character until it gets the entire flag. So fun little challenge. The next challenge is web reguest. It says HTTP requests and libraries are hard. Sometimes they do not behave as expected, which might lead to vulnerabilities. And we're given this URL and a download file. I'm going to open this in a private browser. Cool. So it says request cookies are role guest. Request cookies sending response is guest nope. Okay. Let's look at the source code. We're given a bunch of different files. There's 2 different Docker files and 2 different, I guess, web services that are running. The first one is app.py, and so we saw some of this output. It's a little Flask app. It has an index. It's going to look at some cookies, look at who wrote the code. It's overwriting some cookies. If cookies role is not equal to guest, it's illegal access. Then it's going to send the cookies to the backend. your cookies are, it says someone's drunk, something, something. Cool. We can take a look at the back end. At route who am I? It's going to grab two cookies, the role and the role and really. It's going to compare them, and if we are the admin and really is equal to yes, it'll send out the flag. I'm not sure if this challenge is broken or what's going on, but if you just do document.cookie is equal to role is equal to admin, and then you do document.cookie really is equal to yes, it'll give you the flag. So we just had to set these values. I think what the challenge was trying to show that it's overriding the cookies, but the cookie dictionary doesn't work as expected, and so this shouldn't be possible. Yeah, if cookies role is not equal to guess, it should be illegal access. So for some reason, I guess the request cookies object is a little bit strange, which is what the challenge hint was describing, but you just set the cookies yourself and, just try it. You'll get the flag out. So nice, fun, simple challenge. The next challenge is web zipper. It says, my colleague built a service which shows the contents of zip files. He says there's nothing to worry about. We're given 2 links and a download zip. We can probably guess that this is going to be a zipslip just based off of the name. So let's take a look at what they gave us. There's 2 different Docker files, Docker Compose. So we can see there's a zipper service and a serve service. Docker file for app is just latest Python. Docker file for serve is just latest Python. It's going to be running these 2 files. Cool. So if we look at the app file, so it's a Flask app. Give me your zip file and I'll make it accessible to you. If you post it with the file parameter, it'll read the file. It'll create a new directory within temp. And then if the zip file is there, it'll run unzip on it. Cool. And then from there, it'll tell you what files you found, and it'll give you a port to connect to. Like I said, this looks like a zipslip challenge. So with zipslip, you can zip symbolic links. So this is the solve script, one of the solve scripts. So you just do OS system. So we're going to create a symbolic link to the flag file. So we're going to link all of this up flag to just the flag file. And so that flag is now a symbolic link file. And then we can zip that in. So we're going to do zip, we're going to do symlink. This is our exploit zip file with the flag file, which is a symbolic link. From there, we need to upload it. So this is the upload script. There's no upload form on the website. So we're just going to take that file. That's our exploit script, and we're just going to send it there. So we can do that. Python 3. First, we create the zip file, but it already exists. And then it was Python solve upload. Why is it not? Oh, it was under solve. Oops. Let's go to solve. Then Python 3 solve upload. It'll upload, and it says it puts the files here. I think one of the URLs is slightly broken, so we're just going to copy this manually. So we'll go here. We go to this one. This is the second one. We'll go to our files. It was 16. And we have a flag at. We'll download it. Oh, Chrome doesn't like it. Continue downloading. Where are you? Can we drop it? Here we go. And so, yeah, zip files can be dangerous, so be careful. I guess the only other thing to mention is you had to know where the flag file was, but since they gave us the Docker files, it really wasn't too bad. They put it in the Docker Compose. You can see they mounted flag to the root here, so you knew where the flag file was. Yeah, just fun little zip slips challenge. And that was it. So there were a couple challenges I didn't solve. I'd highly recommend looking at real write-ups, but just to kind of give a hint to what the challenges were about. So there was this lover challenge. This was a Windows executable, just some game where you have to like match tiles or something like that. You can do a bin walk on the binaries and you'll get out a bunch of Lua scripts. And if you look at the Lua scripts, eventually you'll find there's some variable that's kind of setting the indexes where the flags are supposed to be. I didn't actually figure that out. I needed help. I asked in Discord, and she was able to point it out. But in this Lua file, you can match the glyphs and the characters and you'll figure out the flag. Trickster also had a clever idea. They showed that you can actually just change the Lua files within those binaries and rerun the game, and that way it'll actually just show you what the flag is. So very clever. Another one was rain checks. So this was a cloud challenge. In this, they give you these 2 files in exposed user credentials. You're going to get a AWS access key, an AWS secret key, and this other weird token. Eventually you figure out that token is a TOTP code. And then there's this exposed policy, and they show that you need to do MFA checks for all the requests. And so you needed that TOTP code, which I think is what most people got tripped up on, ourselves included. But from there's some lambda functions. You're able to pivot to different lambda functions, and I think they show you that there's this third lambda function that has the flag in it or something. Again, I didn't solve the challenge, but that's just from reading other write-ups. We talked about spygame. The next one, the sound of the flags. If you listen to it, it's some kind of strange sort of like trumpety audio. It turns out the solution was the trumpet is actually doing Morse code. It's pretty good. The music actually sounds like music. But yeah, there was Morse code in that challenge, which we missed. We talked about breaking news. That was the wiener attack. Noble Collector was another hastad broadcast attack. I thought after that you're supposed to do coppersmith because there's like this known preceding plaintext part, but reading up from Discord, it sounds like you could just use like some generalized hastad attack and collect, I guess, the key, which sounds crazy. Then there's also this learning with errors challenge. Only one person solved it. NeoBio, they're too OP. I see them all the time, but I didn't even attempt this one, and I have no idea what it's about. So you'll have to go to Discord and talk to NeoBio about it. And then the rest were the hardware challenges. Those were on-site only, so obviously couldn't participate in those. But overall, like I said, the CTF was a lot of fun. I did only expect to spend an hour, but ended up spending the entire day on it. But had a lot of fun, and I'll see you at the next CTF. Thanks.